Assalamualaikum and good morning. We continue with subtopic in extremum of functions, which is second partial test. So let f have continuous second partial derivatives on an open region containing a point a, b, for which fx equal to 0 and fy equal to 0. For this one, fx and fy are critical points. To test for relative extrema of f, consider the quantity d equal to fxx, fyy minus fxy squared. This d we call as discriminant. We can have four conclusions if we find the discriminant. The first one, if d greater than 0 and fxx greater than 0, so the function f has a relative minimum. If d greater than 0, fxx less than 0, so f has a relative maximum. And number 3, if d less than 0, so it is a saddle point. And lastly, if d equal to 0, the test is inconclusive. The meaning of saddle point is all other points appears in f which are not relative minimum or relative maximum. So we have steps here how to determine the relative extrema, and to show these steps, I will choose example number 1. The question is, find the relative extrema of fxy equal to minus x cubed plus 4xy minus 2y squared plus 1. In order to solve this question, so step number 1, identify the critical points A, B. This step was already shown in the previous video. So to find critical points, the first step is we have to find fx and fy. So for fx, we have minus x cubed plus 4x in the fx function. So differentiate partially for this one, we have minus 3x squared plus 4y. For fy, partial derivative with respect to y, so we have y and minus 2y squared in fxy function. So differentiate both of them. Partially, we have 4x times 1 minus 4y, we have 4x minus 4y. Then we have to let fx equal to 0, so just take the answer for fx equal to 0, first equation, and fy equal to 0, take the answer for fy equal to 0, and this is equation 2. So in here, you have to use your skill in simultaneous equation. What we have to do is we have to solve for equation 2 and we get x equal to y. So this one becomes equation 3. So substitute equation 3 into equation 1 to solve for this one. So replace y equal to x and we get this. Since we have x in both terms, so we can factorize x. So we get this one. And separate them, we have x equal to 0 and we have minus 3x plus 4 equal to 0. So we have x equal to 0 and solve for minus 3x plus 4 equal to 0, we have x equal to 4 over 3. Next, we have to substitute x equal to 0 into equation 3. So we have x equal to y. So when x equal to 0, y equal to 0. What we have to do now, we have to match x equal to 0 and y equal to 0 into a point form. So we have the first point 0, 0. Do the same for x equal to 4 over 3. So substitute x equal to 4 over 3 into equation 3. So we have x equal to y, so y equal to 4 over 3. Then match both values, we have 4 over 3 and 4 over 3. So we have two critical points, 0, 0 and 4 over 3, 4 over 3. So we move to the second step, compute fxx, fyy and fxy. So now we have second order partial derivative. We already have fx, so differentiate again with x, we get minus 6x. And then we already have fy, and then differentiate again with y, so we have minus 4. And we already have fx, we have to differentiate again with respect to y, we have 4. So done step 2. And then step 3, at each critical point A, B, evaluate fxx, fyy, and fxy. For step 3, 4, and 5, we do it together. So step 4, we have to compute discriminant D. And step 5, we have to check for D and fxx. And we have to conclude based on the second partial test theorem at the above. So this is for step 3, step 4, and step 5. So you have to draw a table like this. It must have critical points. So just put you have two critical points, 0, 0 and 4 over 3, 4 over 3. Then you must have column fxx, fyy, fxy. The next column is for D discriminant. So formula for discriminant is fxx times fyy minus fxy square. And then you have to put the conclusion based on second order partial derivative from the previous page. So for each critical points, we have one value for x, the first one, and the second value is for y. For the first critical point 0, 0, so we have fxx and we already get our fxx, which is minus 6x. So we have to write minus 6x and we have to substitute x equal to 0 from the first critical point into this function, and then we get 0 for fxx. Next column, fyy, we already have fyy, which is equal to negative 4 from step 2. So there is no variable x or y, so we just take the value minus 4. And it is the same for fxy. We have a constant 4, so just write 4 in the table. And then calculate for discriminant. So fxx 0 times fyy minus 4 minus fxy square, so minus 4 square. So calculate this one, we get minus 16. And of course, minus 16 is less than 0. Based on this second partial test conclusion, so we know that we have D less than 0. So we have number 3, D less than 0, and the conclusion is saddle point. So write that in your table, meaning that the point 0, 0 is a saddle point. Next, do the same for point 4 over 3, 4 over 3. Calculate for fxx. We get minus 8, which is less than 0. And then fyy equal to minus 4. Fxy equal to 4. And then calculate for discriminant D. We have 16, which is greater than 0. And obviously here we have D greater than 0. And we have fxx less than 0. So refer back to here, we have D greater than 0 in 1 and 2. But in the table, we have fxx less than 0. So we take the conclusion in number 2. So our critical point is a relative maximum. So this is the final answer for example 1.